We'll talk about this application in the second half of the presentation. Not just that, Spark also contributes to train some of our machine learning models that power our recommendation systems. In general, Netflix is a data-driven company. We use data to drive most of our decisions. We collect a lot of data from user interactions on devices and platforms and services that host Netflix. One example where we use this data is A/B testing. So let's say we have a UI change. We don't just deploy the change globally and hope that it works out. Rather, we A/B test it and make sure that it actually improves the experience. The biggest challenge we face is scale. Just to give you an idea of at what scale we operate, I'm going to share with you some numbers. So Netflix has over 80 million subscribers in 190 countries. We support over 1,000 devices, streaming more than 100 million hours per day. As you can imagine, this generates a lot of data. But how much data are we talking about? Our data pipeline processes over 700 billions every day, and we store this in our data warehouse of size 40 petabytes. From this warehouse, we read 3 petabytes and write back 300 terabytes every day. Today, we'll walk you through 3 sections. In the first section, we'll talk about the architecture of our big data platform. Next, we'll delve into the technical challenges we faced while productionizing Spark. And finally, we'll talk about ETL. Okay, let's start with the architecture. So we basically need to answer 2 questions here. The first question is, how do we get data into our platform? It looks like this. So we have 2 data pipelines. On the top, we have our event data pipeline. So this is the data that comes from devices and microservices that run out in the cloud. And this data flows into our Kafka clusters. And we have a process called Ursula, which demultiplexes this data, merges this, and stores it in our S3 data warehouse. This pipeline runs in about a minute. At the bottom is our dimension data pipeline. Most of our live data is on Cassandra, and everyday backups are taken, and we have a tool called Aegis, which reads these backups and then writes it out to S3. In the end, we have both our event and dimension data on S3 ready for processing. The next question we need to answer is, how do we process data? At this point, our data is on S3, which is our source of truth, and we predominantly use Parquet file format. On top of the storage layer, we have our compute layer. We host large Yarn clusters, and Pig, Hive, and Spark all run on top of Yarn. We have dedicated clusters for Presto, and we have some use cases for Druid as well. On top of compute layer, we have 2 services which helps us run at this scale. On the left is our federated execution service called Genie, which helps users submit job to clusters. On the right is our federated metadata service called Metacat, which helps users get to their data. On top of the service layer, we have a whole variety of tools. We have tools to move data around for quality, metrics, auditing, and visualization. At the very top is our interface. We support hundreds of internal Netflix users, and most of them go to the Big Data portal, which is our one-stop shop for accessing big data services. So users can go there, pick a compute engine, and run their job. There are other cool features like schema browsing, S3 access, and so on. The Big Data portal under the hood uses the Big Data API, and users can directly use this API to get the same functionalities in their applications. We also support PySpark and Zeppelin notebooks as well. Here is how our Spark on Yarn deployment looks like. We run over 3,000 nodes on the Amazon cloud of instance type D24X large. These instances have 16 vCores and 120 gigs of RAM. Thanks to Genie, we can run multiple Spark versions on the same cluster. This enables us to check out new features and bug fixes in the recent versions. And I'll talk about this in the next slide. And finally, to make best use of our resources, Spark shares the same infrastructure with MapReduce workloads. So this is how Genie enables multi-version support. Genie maintains the binaries and configuration for every Spark version we support, and when users submits a Spark job, he or she can specify a version, and Genie would use that version to download the application binaries and configuration from S3, and then it would create a sandbox and kick off the job, which would eventually land on our yarn clusters. Okay, let's move on to the technical challenges. The way we are going to do this is we're going to walk you through the life cycle of a Spark application, and as we do that, we're going to talk about the technical challenges we hit. So in Yarn, we have the resource manager process. This is the master process which manages cluster resources. When we submit a Spark application, the first thing that happens is the resource manager is going to create a Spark application master container, and it would launch that. And then the driver via the AM would request for an initial set of executors from the RM, and then the node manager would launch those executors. In a typical Spark job, you might have used the RDD, or the Resilient Distributed Dataset interface. This is a core abstraction in Spark. We had two technical challenges here. One is a limitation of the RDD interface, and the other is a performance optimization. Here's the first one. So recently, we had a use case where we wanted to merge small files. So we tried to use the coalesce method in the RDD interface. But this method merges partitions by a given number of partitions, but we wanted to merge by file size. In Hive, we used to do that by using the combined file input format and then setting the max split size. So we wanted something similar in Spark. So we added support to pass in a custom coalescer to this interface, and then we implemented a size-based coalescing strategy, which is what we wanted. Okay, now let's take a look at the optimization in Union RDD. We noticed that simple queries like select star from table limit 10 was running really slowly against partitioned Hive tables. We found that for each Hive partition, Spark creates a Hadoop RDD, and then it groups all those into a Union RDD. The reason for the poor performance was the sequential listing of those parent Hadoop RDD partitions. The problem became worse for some of our tables which had millions of partitions. We resolved this by computing the partitions of Union RDD in parallel. This fix was good, but there was another important problem in the S3 file system, which impacted listing performance. So in Hadoop, we found that the file system was making an unnecessary RPC call to S3, which is expensive. We fixed it by removing the redundant call, and this fix, along with the previous Union RDD fix, improved our input split calculation performance by 20x, and which resulted in faster job startup. This problem was on the read path. We hit another issue on the write path with output committers. So output committer writes the output of a single task in an all or nothing fashion, and Spark uses Hadoop's output committer, where tasks write to a temporary directory, and then the first successful task attempt's temporary directory is renamed to the final destination. This doesn't work well with S3, because in S3 a rename is basically a copy and a delete. And since we use version buckets, it resulted in having 2 copies of the data, and it's also less performant because it does a copy. Also, S3 has eventual consistency issues. We resolved this by using our internal S3 output committer, which we plan to open source in the future. So here, tasks would write their output to local disk, and then the first successful task attempt's output is uploaded to S3. So this avoids the redundant S3 copy and also eventual consistency issues. So at this point, the driver has finished listing and it has started running tasks on executors. If dynamic allocation is enabled, that would kick in and scale the job's executors up and down based on workload. We've had several major problems with dynamic allocation, and I'm going to talk about 2 of them here. Here's the first one. When dynamic allocation is enabled, we found that reading broadcast data can take a long time. The reason was that executors got the block locations of the driver once during the read, and with dynamic allocation enabled, replicas can be removed, which resulted in stale entries in the block location list. Here is a log from our production application, which shows that reading a broadcast block can take as long as 17 minutes. So we set the retries to 3 and the gap between retries to 5 seconds. So each failed attempt would take 15 seconds. Here you see there are about 70 failed attempts. And if you do the math, it takes about 17 minutes to fetch 1 broadcast block. We fixed this on the executor side. Now executors refresh the block locations from the driver after multiple failed attempts. So the second problem we had was with locality optimization. We noticed that a Spark application failed due to timeouts. We debugged this, and we found that the Spark application master would cancel and resend container requests if either the locality preference is no longer needed or if the locality preference is not set. Problem is we use S3 and there's no locality information set on S3, which was causing that thrashing. So we fixed this by not canceling container requests without any locality preference. Now, Nazi will continue talking about the technical challenges.
Yeah, thanks. Thanks, Ashwin. Hey, everyone. So now at this point of execution, the tasks start running in the Spark executors, and now they need to read the data from S3, which is in Parquet format, and then they run the data flow, and then if they need to, they write back the data in Parquet format again to S3. So this is the part where the Parquet rewrite path comes into the play, and we had 2 main challenges in the Parquet rewrite path. So the first one is actually a performance optimization that we have been experimenting with recently, which is what we call dictionary filtering. So in the previous presentation, Owen mentioned some of the details of the Parquet format, but I would like to recap it a bit before describing the optimization itself. So in Parquet, Parquet is a columnar file format, and the data is organized in a hierarchical way. So at the top of this hierarchy, you have row groups, which are basically groups of rows. And then within each row group, Parquet defines column chunks. So you have a column chunk for every column in your data set. And then within every column, you have multiple pages, which are the smallest unit of data that Parquet encodes and compresses before writing to disk. And when you write the data with Parquet to disk, you will see something on the right, where the columns are contiguously laid out on the storage. And during the read-write process, Parquet supports a number of different encoding and compression algorithms, like run-length encoding and dictionary encoding. And here in this optimization, we use the dictionary encoding. And how it works is, when Parquet writes the data, instead of writing the raw values, it assigns integer index values to every unique value in a column. And then instead of writing the raw value, it writes these integer values and also stores the dictionary together with the data, as shown at the bottom of this slide. So when you go back later, read these integer values, you can load the dictionary and do a lookup from the dictionary to get the raw value back. And how this optimization works is, it can be explained with a simple example. So let's say you have a query like select star from T, where state is California, and assume that state is dictionary encoded. And what an engine can do with this optimization turned on is, it can just load the dictionary itself instead of loading the entire row group, and then do a lookup in the dictionary to see whether the state value California is in the dictionary. If it is not in the dictionary, this means there's no way that a row in this row group will match this predicate. So it can simply skip this row group and then move on query processing with the next one. So this will save a lot of CPU and I/O time, and which will result in significant performance improvements, as we show here on the slide. So this is showing some numbers from some of the performance experiments that we did with this optimization. And on the vertical axis is the average wall clock time across multiple runs. And on the horizontal axis, we show different cases where we keep the dictionary filtering off, and then we enable it with 2 different row group or split sizes. So what we find out is, with a split size of 64 max, we were able to skip a good amount of data while processing this particular query, and this resulted in around 8x speed up. And if we keep increasing the speed up, we were able to skip even larger chunks of data while processing the query, which is resulting in almost 2 orders of magnitude of improvement. So the overall, the message is, if you have queries that has predicates against dictionary encoded data, you can benefit from this optimization. So this optimization is not released yet. It will be released in Parquet 1.9. And enabling it in Spark is a little bit involved. So this slide shows that. I won't get into all these details, but you basically need to enable some filtering parameters and disable schema merging. And that was on the read path, that optimization. We had another issue on the write path, which is with dynamic partition insert. So typically when you do partitioning with Spark, when you do partitioning with Hive, it is static. That's you assign static values or hard-coded values to your Hive partitions. But with dynamic partitioning, that value that you assign to your partitions are determined during the execution time. And if you have a large number of these partition values, it can cause memory issues with columnar file formats such as Parquet. And the reason for the memory issue is Parquet needs to buffer entire row group of data before laying out the columns contiguously on disk. And what this means is, when you are writing, dynamically writing these partition values, you need to keep a large number of Parquet writers open, which will accumulate these buffers in memory and eventually leading to out of memory situations on your executors. And Spark already has some sort of problem, some sort of solution for this. And the solution works reasonably well, but has some limitations. And the solution is, before writing the data to disk, Spark sorts the data based on the partition key so that the data is clustered by the partition key itself. And then Spark keeps a single Parquet writer open and then writes a cluster and then goes to the next cluster, closes the writer and opens a new one. So it only keeps a single writer open to cap the memory consumption on the executors. And the limitations that we have fixed are the following. So the first limitation is, if the user has already sorted the data based on the partition key, Spark blindly resorts it again unnecessarily. So this is a complete waste of time. So we get rid of the second sort by looking at the logical plan. So if the user has specified a sort operation, we can look at the logical plan and deduct this and then skip the second sort. And the second limitation that we fixed is, so users typically insert a repartition operator before writing the data because they want to control the number of output files when they write the data. So we exposed high-level APIs in the data frame writer interface, so they can specify the number of files they want in the output, and then we insert the repartition operators under the hood for them, just for the convenience of for bringing convenience to the API. Now the tasks have written the data back, so they are finished, hopefully job finished successfully. And now you may want to tune the performance of your application or gain some insights into the execution. For that, you need to go back to the history server to understand, let's say, how the individual tasks perform, like their runtimes, their input data sizes, whether there were skew or not, or whether there was a lot of garbage collection. So you go back to the history server, and you are surprised to see that your application, which has just finished, doesn't show up. So in a case, with some production application, we have seen like an application did not show up for multiple hours just after it finished. So we started debugging the root cause of this. And what we found out is there is only a single thread that's processing the application event logs in the Spark history server. So what this means is, if you have an application that has a very large event log file, that will keep that thread busy, and other applications will not show up until this one is processed. And this is not really an edge case. So we have like many production machine learning applications, which are iterative applications, which can easily generate log files of tens of gigabytes in size. And the solution is sort of easy. We need to parallelize the event log processing logic, and we did that. And we also did some experiments to see whether GC tuning may help, and we found like if we move to the G1 collector from the CMS, the concurrent mark and sweep collector, and also if we expand the young generation size, we found that the time from when the application finishes to when it shows up reduces dramatically. Now let's take a look at ETL. So at Netflix, we run around tens of thousands of jobs, ETL jobs every day, and most of these jobs are written in Apache Pig. There are some Hive jobs, and recently we started seeing some Apache Spark jobs as well. So when we started this investigation, one of the first questions that we asked is, if we make a move from Apache Pig to Spark, will we get on par or better performance with it? Will there be a performance hit if we do that? And for that, we started looking at some of our typical Pig ETL jobs. And then we have implemented those jobs in Spark using the data frames API to do some performance investigations. And this is one of those jobs. So this pick job loads data from 6 different data sources, runs some basic transformations on it, and then runs a sequence of joins one after another, and then writes the data back to S3. And then this graph shows the performance numbers for that, for that application. And on the vertical axis is the average wall clock time across multiple runs. And we here show 3 cases. The red bar is Apache Pig, and then we have Spark, which is the Scala data frame implementation for this job. And then we have PySpark, which is the Python data frame implementation for this job. And then with Scala, we found that we get around 2.5x speed up. And the reason for this speed up is twofold actually, but there are many other reasons, but the major improvement comes from 2 factors. One is when you move from MapReduce to Spark, you get rid of the JVM launch overhead. So when Spark launches a task, it doesn't need to launch a new JVM from scratch. It just does an RPC call, and the task is serialized over the wire, and the thread just picks it up and runs it. So that's the first factor that contributes to this improvement. And the second reason is Spark has better physical operator implementations than PIC, because Spark can generate bytecode for a good chunk of these plans, and also it lays out the data more efficiently in memory thanks to all these changes that the project Tungsten brings. And then we looked at the Python implementation performance. It's still better than PIG by 2x, but it's slightly slower than Scala. And the reason is we had some UDFs, user-defined functions, in this PIG pipeline, and UDFs cause data serialization and deserialization between the executor JVM and the Python VM, which consumes a lot of CPU time, so which results in a slowdown in this application. And this is another job that we moved over to Spark for testing purposes. This job loads from 3 different data sets, runs some transformations on it, and co-groups 2 of those, and then runs 2 joins, and then sorts the data and writes it to S3. Again, we got similar results. We get, with the Scala implementation, we get around 3x performance, 3x speed up. But this time, we got slightly worse performance with PySpark compared to Scala implementation. And the reason is the increased number of UDFs in this pipeline. So if you have more UDFs that were doing heavy processing, so there was a lot of serialization and deserialization going on. So overall, we have other results showing similar speed ups with Spark, but we don't show them here for brevity. But overall, at this point, we were convinced that moving to Spark will bring us some performance on the table. So the next step for us was to implement some tooling for our users. So if a user wants to create a new Spark application and productionize it, he shouldn't be doing the heavy lifting, and he shouldn't be implementing all the tooling for himself. Instead, we should provide these tools for making their lives easier. So the first step, so we ended up with this high-level productionization workflow, where in the first step, they start prototyping their applications. They start writing the code of their Spark applications. They can use their favorite IDEs, or they can use the Zeppelin and PySpark notebooks that we provide in our infrastructure, or they can just use the tools that we have on our gateways. And during the prototyping process, we created for our users some template projects, some template Spark projects that they can use, like providing common classes, common user-defined functions or base utilities that they can use to get them started quickly. And also we provide them a number of plugins like Gradle plugins or IntelliJ plugins that they can use during development, so that with those plugins they can just submit their applications through Genie to the Yarn clusters, which will make their testing easier. And after prototyping, once they have something concrete, they need to build a binary artifact out of it. So for that, they can use the Jenkins job templates that we created for them. And they can simply use these templates to build their applications and create these binary artifacts. And then again, using the same templates, they can upload these binary artifacts to S3. And then once the runnable artifacts are in S3, they can go to the Atomic Scheduler interface, which is the production ETL scheduler we use, and then they can use the job templates that we created for them and then point to these runnable artifacts on S3, and then Atomic will later schedule these jobs, download the artifacts from S3 and schedule these jobs through Genie to our production clusters. So now that we have the tooling in place, various teams have started implementing new applications, and I would like to conclude this section with 2 of these production applications. And the first application is Yogun, which the application owners define as a rapid innovation platform for targeting algorithms. So what this means is, say Netflix released a new original TV series, and we want to promote this original TV series to a subset of our users. And the question is, which subset should we promote this new title to? And the answer is determined by targeting algorithms and models. And previously, this team owning the organ was using a mix of pig and hive scripts for experimenting with targeting algorithms. But pig and hive scripts are really hard to maintain, and they are usually slow to experiment with if you run a lot of experiments during the day. So when we productionized Spark, they started migrating over their pig and hive scripts to Spark, and they got some good results with it. For example, previously, what was taking tens of hours to run some similarity calculations against our entire user base is now only taking 5 hours. Or similarly, it now only takes just 10 minutes to run some similarity calculations against a small subset of our user base for rapid iterations. So overall, for this specific targeting use case, Spark really helps us innovate and experiment faster. And the second application that I want to mention is the ARO application, the adaptive row ordering application that Ashwin mentioned at the beginning of the talk. So ARO is a very complex pipeline comprising a number of different jobs, and what it does is to provide a personalized ordering of the rows of titles that you see in the main Netflix page. And Spark takes part in this pipeline towards the beginning, where it helps creating the feature data for downstream consumption. And in particular, what it does is it enriches the page and row level feature data with the user's play history and runs some transformations on it and then passes that to the downstream jobs. And this job is slightly on the bigger side, so it has more than 10 stages and runs tens of thousands of tasks and processes several terabytes. So at the beginning, when we tried to productionize this job, we had a number of performance and reliability issues at this scale. So we started working with the application owners and made some changes to their source code, and also started tuning some of the Spark parameters to make the application reliable. And finally, this application runs pretty reliably and performant way in our infrastructure daily. So I'd like to conclude the talk with some of the future work that we have in mind. And the first item is improved Parquet support. So Spark already has pretty good Parquet support, but where we want to get eventually is to have a read-write path that works at our scale in a performant and reliable way. So we will continue working on the optimizations that I mentioned in this talk, and also we'd like to spend some time on the reliability aspects as well. And the second item is better visibility. So Spark has a nice UI that you can look at during the execution, or you can look at the history server after the fact, which provides a lot of nice statistics about the tasks and stages and everything. But what we want to do is to get that execution data into our internal data pipeline. So we may want to go back and run some analysis on the historical executions and get some insights into it. And the second aspect of better visibility is to get some lineage information. So we'd like to know which users owns which applications and which applications depends on which data sets. So this sort of information is pretty useful in complex data warehouses. And the final item is exploring new use cases. So this talk is mostly about ETL, but we have a number of other use cases at Netflix that we care about. And one of those use cases is interactive and semi-interactive use cases, where users may submit queries from their BI tools such as Tableau and may expect some sort of interactive performance. And the second use case that we care about and that we want to explore is offering streaming as a service in our big data infrastructure. And for that, we would like to explore whether we can use Spark streaming in a shared yarn cluster with dynamic allocation turned on. And the final use case that we want to investigate is the feasibility of moving our internal merge pipeline, which is merging small files using Apache Hive right now, to whether it makes sense to move it to Apache Spark. So that's the third use case that we want to explore going forward. So summing up, so we have walked you through our experience with Spark so far on Yarn for ETL processing. So in the first part, we talked about the technical challenges and the solutions we provided, which are mostly available in Spark 2.0 preview release. And in the second part, we talked about ETL, in particular the performance investigations that we did, the tooling that we built for our users, and some of the production Spark applications that our teams at Netflix have built. So hopefully this has given you some idea about our experience with Spark so far. So with that, we'd like to thank you all again for attending this session, and we'll be happy to take any questions you have. Yeah, thanks.
Why are you using Parquet? I mean, is there a specific reason for that? Why not
Parquet?
Orc or Avro or any other file format rather
So
than Parquet?
back in times when the team evaluated different file formats, Parquet was performing reasonably good compared to other formats, and it has nice tooling support like peak support and high support. All the tools in the Hadoop ecosystem was supporting it. So the tooling support, compatibility, and the performance and reliability was an aspect to pick it up. You should get the mic, I guess. Yeah.
Can I ask a question on Spark Streaming? Yeah. So in Spark Streaming, suppose if I'm getting the data from Flume or Kafka, so what is the best practice? Like I want to do the log analysis, say for example, and find out how many counts are there. So combining both the collecting the data and doing analysis is the best practice, or separating them into different Spark applications. Like I collect the data in one Spark application, in second application I do the log analysis. If that is true, second approach is true, what is the best way to communicate between the applications?
So I don't have much experience with Spark streaming,
Okay.
but the second approach sounds complex to me, like having two different applications and then unify the outputs. So
Okay.
I would probably not do it with two applications. That's what I can say.
Okay,
Yeah.
got it.
Just interested on your talking about the S3 issue that output committer things. Can you share a bit details and the plan and contribute to Apache, because I'm from the Apache Yarn community? So
Yeah, we
quite
do
interested.
have plans to contribute it back, and hopefully in, I think Q4 we might target it. I need to talk to my manager about that, but yeah, hopefully Q4.
Is there any details how to handle inventory consistency of the S3 thing?
It's just that you write the output to local disk, and then you upload the first successful task attempts to S3, which would take care of eventual consistency issues.
Since this talk is about a petabyte by scale of data set, what's the largest data site file size you have processed using Spark? Because 1 petabyte data has 10 million HDFS blocks, so that's a lot. And I'm just wondering, so what's your experience?
I can. Yeah, the largest application that I have seen in production was processing several terabytes that's scattered around thousands of files. So it's not like just one file holding an entire petabyte. So it's chunked up in blocks sitting on S3. So the largest that I have seen in prod was several terabytes by Spark, yeah.
Just follow up, how long does it take to do that? It's like,
It takes to process several terabytes?
yeah,
I mean, that
6 hours, 24
that
hours.
job was taking several hours to run. I don't remember the exact number, but it was taking several hours because it has a large number of stages. It was taking long to process it, yeah.
Okay, so my question, can you explain again how you do the customized closes? You collapse the partition into one, and you said you don't need that, you need the
The custom coalescer?
Yeah, by size?
Yeah, by file size. So
Yeah.
we added support to pass in a custom coalescer to the coalesce interface, and then we implemented a size-based coalescing strategy to do this by file size, to merge by file size.
What use case you need that?
Oh,
why you need that?
The merge use case.
Yeah.
Do you want to talk about the merge use case for that?
Yeah, so we wanted to merge, we have a large number of small files, and we want to merge those small files into larger files because on the read side, it hurts performance when you have small files. And we were looking at the RDD interface, and then we looked at the coalesce. It merges the partitions, but you can specify only the number of partitions that you want to end up with. So when you do that, you will end up with an unbalanced distribution in the output. So it wasn't really merging the partitions by size properly. It was just, you can just set the number of output files. But with the change we did, we can now properly merge these files by size so we get evenly balanced files in the output. Okay, we can discuss offline.
Have you tried peak on test or another peak side optimization or something?
No,
Okay.
some time ago we looked at pig on tails, but yeah, we did some benchmarks, so I don't know the exact numbers for that. But for now, we don't have pig on tails
Okay,
in our
thank
infrastructure.
you.
Yeah.
Thank you.
So we have faced a similar issue you faced for the file output committer. I wonder if you had changed the version 2 file output committer algorithm to 2 and tried it.
Which one? The
So there is a MapRed config. It's called the Hadoop MapReduce
I know.
file output committer algorithm. Did you try the version 2?
Oh, that's a version 2? Okay, I
Yeah.
haven't checked it out.
Oh, okay.
You think that fixes this problem?
It did for us. So we were seeing about 10 minutes or so. It reduced it to 30 seconds or a minute. That's the file output committer stage.
It wasn't, our problem was not related to performance mostly. It was like,
okay, the timing
the redundant S3 copy and
it is
performance
similar
too
for us
because
as
it
well.
does a copy. Yeah.
It's
And
about-
one last question, sorry. Node locality. How did you guys solve that for the S3 file system?
Oh, so we basically don't cancel container requests which have no locality set. So S3 doesn't have locality set, so we don't cancel it.
So basically the driver was keeping track of the container requests, and then as an optimization, it was just canceling the in-flight requests and then rescheduling them so that hopefully they will land up on a node with data local. But with S3, we have all these container requests had no locality information, so canceling and rescheduling was for nothing. So we basically don't do it for container requests with no locality information.
Just a quick question regarding YARN containers. On a regular HTTP cluster, when we assign YARN container sizes, all the Spark jobs that are using the container size have a limit to that container capacity, right? How did you guys manage to use the entire cluster capacity within a container? How did you how did you configure container size to run Spark jobs?
So currently, like we mentioned, we are running on D3. We have 16 cores and 120 gigs of memory. So MapReduce containers are configured with 2 gigs, I guess 2 gigs, and Spark is configured with 10 gig of memory. And we can run many of these containers. So we are, I guess, we do put a limit on the number of containers that we can run.
There's no limit.
So if,
I mean, it's just that as much as.
Yeah, as much as it lands on. I mean, we have 2 and 10 gig allocated per MapReduce and Spark job.
Yeah.
Spark container.
What HDFS block size you guys use?
It's 128 megs.
120. Quick question. So you use any external table on the S3, or I kind of answered that question with the other gentleman, but do you ETL the data into HDFS, or you still access from S3 on the fly?
Yeah, the jobs are reading directly from S3. They don't download it to HDFS. They just read it from S3 and run the computation and write it back.
Okay, thanks.
Regarding the multiple versions of Spark in the YARN, did you face any Classpath issues where it was contradicting with the cluster installed Spark, where say the cluster was installed with 1.5 and the user wanted 1.6?
You mean the Spark version?
Yeah, Spark version.
So we don't install Spark on the clusters.
Okay, so binary ship.
Yeah, the binary is like shipped, or it's staged on S3 and then it's pulled from the executors and driver when needed.
Okay, so because like I had faced that Classpath issue.
Yeah.
I think we have time for one more question.
I think you use the dynamic allocations. So do you know what's your number of executors actually runs when you run your largest file, like say your multiple terabytes data? Because I know you have 3,000 EC2 instance. That's a lot of instance. And you said your performance runs 10 minutes to 2 hours. So that sounds a little bit long. I just wondering
what's the question now?
What's the number of executors you've seen in your Spark jobs?
The number of executors. Yes. So we set our max executors to like 500, which is our like sort of fair share for a user in all of our users list. So we have seen like it vary from like 0 to 500 based on the number of tasks that run on each stage. So it like expands and shrinks based on the workload.
Okay, so 500 because you have 3,000 EC2 instance.
Yeah.
It's
500 is like.
But 3,000 machines are shared by a number of users for a number of different applications, so we cannot allocate everything
to Spark, right? So the users still can go above 500, they can override that, but then we have enabled preemption, so they might be preempted. If they're okay with that, they can override the 500 setting and run as many as they want.
And then they will eventually hit their fair share limit. Then the Yarn scheduler will not allocate any containers to that job.
Yeah.
Great. Thank you very much. That's all the time we have. Thank you.
Thank you.